Good morning, students. Right, I welcome you all for this another session. Okay, hope you are done well in first internal assessment. So after the internal assessment, again we're going to start with the video lectures. Now, in the previous session, we have studied analysis of singly reinforced beam, and again we have considered the problems on crack width calculation and deflection calculation. Now let us start with module 2 only. Right, in module 2 already we have completed singly reinforced beam, analysis of singly reinforced beam. Now let us consider in the same module, that is analysis of doubly reinforced beam. Okay, so first we'll see what this doubly reinforced beam, then where this doubly reinforced beam is provided, okay, and how to analyze the doubly reinforced beam. Okay, so as the name indicates, doubly reinforced, so the reinforcement is provided in both sides. Okay, doubly means both sides, that is reinforced concrete beams provided with steel reinforcement on both tensile and compression side. Okay, as we know, the beam is divided into two zones. So this is a neutral axis. So below the neutral axis it is a tensile zone, and above the neutral axis it is compression zone. So if you are providing main steel, okay, that is the reinforcement provided both tension zone as well as compression zone. In both zone you can see the main reinforcement. The number of bars may vary, but both the sides the reinforcement will be provided. So such a beam where you can see the reinforcement on both the zones, that is called as doubly reinforced beams. Okay, so the beam in which reinforcement is provided in both the zones, that is tensile zone and compression zone, so such a beams are called as doubly reinforced beams. So in singly reinforced beam you can see only the main bar at the bottom. Okay, but here top also main steel is provided. Okay, so such beams are called as doubly reinforced beams. Now, now see here in this sketch, this is a doubly reinforced beam. The main steel provided in the tension zone. So this is the steel, and this steel is called as tensile steel. Okay, so it is provided in the tension zone. It is called as tensile steel, and at top also main steel will be there. This is called as compression steel. So this is provided in the compression zone. This is compression steel, and this is tensile steel. Okay, both are main steel only. Okay, so the main steel provided in the tension zone is called as a tensile steel, and in compression zone also main steel is provided, and this is known as compression steel. And where this situation arises means where you can see the doubly reinforced beams. Okay, so the situations in which the doubly reinforced sections are used as follows. Okay, so these are the situations in which we need to provide the doubly reinforced beam. First one is from architectural or any other construction problems, the depth of beam is to be restricted. Now this is important thing. Now when you design the beam means after calculating all the bending moment, and finally steel will be calculated. So depth is also calculated. Now depth is so much required. So in that case, if the depth is more, okay, if you provide depth more, right, so from architectural point of view it will not going to look properly. So you have to reduce the depth. Okay, depth will be restricted or depth will be reduced. So in that case the beam what we are going to provide here is doubly reinforced beam. So from architectural or any other construction problems, the depth of reinforced concrete beam is to be restricted. When the depth is restricted or when you reduce the depth, then you are going to go for the, by reducing the depth we are going to provide steel at the top also. So then that will considered as doubly reinforced beam. Okay, if you want to reduce the depth, okay, So just depth will be reduced, and whatever the steel, total steel is calculated, that will be provided bottom also and top also. Then that beam is considered as doubly reinforced beam. Okay, remember, the first situation is when you want to reduce the depth of the beam, then doubly reinforced beam is provided. So reduce the depth, so steel will be distributed both tension zone and compression zone. Okay. Second, in some cases bending moment at the section changes. When there will, suppose if there is a changes in the bending moment or variation in the bending moment, then we need to provide the this doubly reinforced beam. So where this situation arises, where the bending moment changes from point to point, that is, first one is due to moving loads. Okay, in continuous beam, if the beam is continuous and the load on the beam is moving. So for example, if you see the bridge, okay, so bridge deck beam, the beams provided in the bridge construction, those are called as the deck. Okay, so there always the vehicles will be moving on the bridges, so those are considered as the moving loads. So in such cases, okay, so the bending moment will going to changes from section to section. So in that case we need to provide the this doubly reinforced beam. So in precast members means, so precast means already casted beams or casted members. So already the beam is casted, and we're going to transfer this beam to the site. Okay, so then in that case precast members also, during transportation and during handling, so the bending moment changes from section to section. Okay, so in that case we need to provide the this. And other thing is another important thing is in members of frames. So right now you don't know about these frames, but in multi-storied structures, the frames will going to form. So in these frames also bracing members. Okay, so inclined members we normally call it as bracing members. So due to changes in the direction of wind load, so when you consider the high rise buildings, wind load also will going to consider in the calculation along with the other loads. So during this wind loads, so bracing members, that is inclined members in the frames, are also subjected to changes in the bending moment. So in all these cases we go for the doubly reinforced section. And next situation is to improve the ductility of beams. Okay, in earthquake regions. So especially in the earthquake regions, when the earthquake happens, so your building must be ductile, as far as possible ductile. Normally we classify the materials into two parts. One is brittle materials and another will be ductile materials. So as far as possible, the building or the beams should be ductile. Okay, so in earthquake regions, so to improve the ductility of the beams, we are going to provide the doubly reinforced beams. Then to reduce the long-term deflections, already we have seen that long-term deflection. So to reduce the long-term deflections, we are going to go for the doubly reinforced beam. So one is when you want to reduce the depth of the beam, okay, so we provide the doubly reinforced section, and where the bending moment changes from section to section, doubly reinforced beam is provided. To improve the ductility of beams in earthquake regions, doubly reinforced beam is provided. And to reduce the long-term deflections, doubly reinforced beam is considered. Okay, so these are the situations in which we need to provide the doubly reinforced beams. Now, how to analyze this doubly reinforced beam? Okay, so as simple, doubly reinforced section consists of two parts. Now, you will going to divide this beam into two parts, one by one. First, we'll consider it as a singly reinforced section. Okay, singly reinforced beam with restricted depth. Okay, so with restricted depth, we'll consider this as a singly reinforced beam, providing the limiting moment of resistance mu limit, which is less than design moment. Now, if you consider the total beam as a doubly reinforced beam, okay, so what first we'll consider? First, consider it as a singly reinforced beam with reduced depth Okay, depth will be reduced means the moment will going to be considered. So what is the total moment? Total moment will be mu. Now see here, this is a doubly reinforced beam. So main steel in the tension zone, main steel in the compression zone. So this is doubly reinforced beam. So what moment it has to be registered? It has to register the total moment of how much? Mu. Okay, the moment registered by this doubly reinforced beam is mu. So out of total mu, okay, out of total mu, first I will going to consider this singly reinforced beam. Okay, first I will consider this as a singly reinforced beam with moment is how much? This singly reinforced beam has to take maximum moment of how much? Mu limit. Okay, so for this mu limit, we will going to provide steel. So out of total steel, so this is AST1. Now see, total steel is in the tension zone is how much? AST. So out of this AST, so consider singly reinforced beam, it will going to provide it AST1. Okay, so this AST1, because of this AST1, it will going to resist how much moment? Mu limit. Out of total mu, this beam will going to resist mu limit. Now see here, only steel is provided at the tension zone, no compression steel here. So this beam is considered as singly reinforced beam. Okay, so first consider it as a singly reinforced beam with restricted moment. So out of total mu, this will going to resist how much? Mu limit. So for this mu limit, we are providing steel at the bottom. Okay, now next. Now what is the remaining moment? Total is mu. Okay, so mu and this singly reinforced beam will going to be considered or registered how much? Mu limit. So mu minus mu limit. So this is the remaining moment. Okay, so remaining moment will be how much? Mu minus mu limit. So total is mu. Out of mu, the mu limit or the moment taken by this beam, singly reinforced beam, is mu limit. So for the remaining moment now, for the remaining moment, we will going to provide this beam. This is called as steel beam now, right? So this is called as steel beam. Steel beam means don't under the impression that it is completely steel, no concrete is there, right? Not like that. Okay, concrete will be there, but its effect will be neglected. Okay, now this is singly reinforced beam with AST1. Out of AST, this is AST1, remaining is provided here AST2. Okay, at the bottom AST2, and to balance this AST2, okay, and AST1, okay, we will going to provide ASC. See, can you see this ASC? This is compression steel. Okay, so this is singly reinforced beam. Okay, then with the restricted moment, that is mu limit, this beam will going to resist how much moment? Mu limit. And here remaining mu minus mu limit, this will going to be resisted by this beam. So this is singly reinforced beam plus steel beam. Totally we will going to get this. So see, this singly reinforced beam plus this steel beam. Now see, AST1 here, AST2 here. If you add these two, AST1 plus AST2, will get AST. Then this ASC we can see here. Okay, so this is the beam, or this is a section in which we can see the reinforcement, right, bottom, as well as this compression steel at the top. If you add these two, see, if you add these two, the total doubly reinforced beam we will going to get. So concrete is there here. Okay, don't worry. Okay, so right, so this is doubly reinforced beam. Now as usual, now you can see width of the beam, then capital D, overall depth of the beam, then this is AST, area of tension steel, this is ASC, area of compression steel, then this is effective depth. Then see, this compression steel is provided at an effective depth of the effective cover of D dash. So what is D dash? Small d dash. It is the cover from top to the center of compression steel. Okay, this is D dash. Okay, so now distance between these two reinforcement is how much? D minus D dash. So D minus this D dash will give distance between center to center distance between these two steels, that is D minus D dash. Now again this is a stress diagram. As we know, this is singly reinforced beam. Okay, so what is the force in the tensile steel? That is 0.87 Fy. This is stress, and area of steel is AST1, that is 0.87 Fy AST1. So stress 0.87 Fy is the stress and area is AST1. So stress into area will give force in this steel. Okay, similarly force in this concrete. Now here concrete is there, so it is 0.36 FCK is the stress, area is B into XU. Okay, so this is compressive force in this concrete, this is tensile force in this steel. This is singly reinforced beam plus doubly reinforced beam. Now again as usual, what is the force in this steel? 0.87 Fy, stress into area is AST2. So 0.87 Fy AST2. Then force in this steel, compression steel. So stress into area. Okay, so stress is FSC now. So stress in this compression steel is FSC into what is area? ASC. So FSC into ASC is the force in this compression steel. This is the force in this tensile steel. Okay, right. Now referring to this figure, MU. What is MU now? MU is the total moment, ultimate moment or ultimate flexural strength of the doubly reinforced beam. So MU is the total strength of this doubly reinforced beam. So out of this total MU1, okay, MU1 is nothing but MU limit. Okay, MU1 is equal to MU limit. So that is the moment taken by this singly reinforced beam. This is limiting or maximum moment of resistance of singly reinforced beam. So out of total MU, this beam will going to resist how much? MU1 or MU limit. Then MU2, this is the moment of resistance of this steel beam. This is considered as steel beam. Moment of resistance of steel beam, neglecting the effect of concrete. Here concrete is there, but the effect of concrete is neglected. If you neglect the concrete, what is remaining? This beam is with ASC and this and AST2. Okay, so this is considered as steel beam. So total MU, that is resistance resisted by the doubly reinforced beam, that is equal to this singly reinforced beam will going to resist MU1 or MU limit, then this will going to resist MU2. So if you add MU1 plus MU2 is equal to this total MU of this doubly reinforced beam. Then what is MU2? How will calculate MU2 now? Moment means what? MU2 means this figure you have to consider. MU1 you will going to get, or MU limit you will going to calculate from this figure, and MU2 will going to calculate from this figure. What is M? M means moment. Moment means force into perpendicular distance. Force into perpendicular distance will give moment. So what is the moment here now? There are two forces, right? This is a force in the compression steel. This is force in the tensile steel. So distance between these two is what? D minus D dash. Now I want to calculate a moment at this point. What is the moment at this point? Force. Force is what? FSC into ASC into perpendicular distance between this force and this point is D minus D dash. So MU2 is equal to, okay, MU2 is equal to FSC into ASC. This is a force. Stress into area is force. This force. So force into perpendicular distance, that is D minus D dash. So FSC into ASC, D minus D dash. So from this we can calculate MU2. So how will calculate MU1? MU1 is the maximum limit, that is MU limit. Okay, so MU limit you will going to get from this, and MU2 will going to calculate from this. Add these two, MU1 and MU2. Finally you will get MU. that is ultimate moment of doubly reinforced beam. So then mu is equal to mu1 plus mu2. mu1 means mu limit, okay, mu limit plus mu2. Then from this figure you can see FSC. What is FSC? The stress in compression steel corresponding to the strain reached by it. So this FSC. Okay, FSC is what? FSC is the stress in the compression steel. Stress in the compression steel. Okay. Now ASC. ASC is area of compression steel. D as usual, effective depth of the tensile steel. Then D dash, depth of compression reinforcement from compression face, that is from the top of the beam to the center of this compression steel is D dash. Then AST1, area of tensile reinforcement for singly reinforced beam. See, area of tensile reinforcement for this singly reinforced beam. Then AST2, area of tensile reinforcement required to balance the compression steel. So to balance this compression steel, the reinforcement at the bottom required is AST2. So total AST is what? This total AST is equal to AST1 plus AST2. Okay. Now how to calculate moment of resistance now? Doubly reinforced beam, mu, total mu. So according to IS 456-2000 code, the following procedure is used to compute the ultimate flexural strength or moment of doubly reinforced section. So remember these steps, these 4 steps. First one is calculate the limiting moment mu limit of singly reinforced section. So see here. First we will calculate mu1. mu1 means mu limit. So maximum moment of limiting moment of resistance of singly reinforced beam. So how to calculate mu limit? There are 3 options. Okay, one is depending upon this Fe2 grade of steel. So if it is Fe250, mu limit or mu1 is equal to 0.148 FCK BD square. If it is Fe415, okay, it is 0.138 FCK BD square. Then if it is Fe500 grade steel, then mu limit is equal to 0.133 FCK BD square. So first see which grade of steel is given, and depending upon that we have to calculate either this or this mu limit. Any one formula we are going to use. So this will going to give mu limit, or it is also mu1. Okay. Then calculate AST1. Okay. Calculate AST1. Now see in this figure. AST1 is there now. So how to calculate AST1? Okay. Now see here. The force is what? Stress into area. 0.87 Fy AST1. Now see here. 0.87 Fy AST1 is equal to this. Now there are 2 forces in this case. One is a force in the steel, that is tensile steel AST1. 0.87 Fy AST1, this is a force in the steel, and this is the force in the concrete here. So what is force? 0.36 FCK B into XU. Equate these two. Okay, for equilibrium these two must be same. So these two will going to form the moment. So 0.87 Fy AST1 is equal to 0.36 FCK B into XU. Equate these two. We are going to get like this. 0.87 Fy AST1 is equal to 0.36 FCK B into XU. So this is what XU. XU means here we are providing the limiting moment of resistance, maximum moment of resistance. So this XU becomes XU limit. Okay. So XU becomes XU limit. So equating these two, so we can calculate AST1. So therefore AST1 is equal to what? 0.36 FCK B into XU limit divided by 0.87 Fy. Okay. Then once if you get AST1, next calculate AST2. What is, how much AST2? So AST2 is equal to total AST. Okay. This total AST minus AST1 will give AST2. Okay, AST, total AST minus AST1 will give AST2. Next, now calculate ASC. Calculate ASC, that is area of compression steel here. So how to calculate this ASC now? Again, there are two forces. Okay, one is this 0.87 Fy, AST2. 0.87 Fy is stress into area is AST2. Then here FSC into ASC. Stress is FSC, area is ASC. So there are again two forces. Equate these two forces. That is 0.87 Fy, AST2 is equal to FSC into ASC. Equate these two. 0.87 Fy, AST2 is equal to FSC into ASC. So from that ASC is equal to this term. But here first you have to calculate this FSC. That is stress at the level of compression steel. How will calculate FSC? FSC will be calculated like this. Okay, FSC is equal to 0.0035. This is strain. Okay, strain in the steel. 0.0035 into bracket XU max or XU limit, both are same. XU max minus D dash whole divided by XU max into ES, Young's modulus of steel. Okay, now how you have got this? FSC is what? Stress. Okay, so stress divided by strain. See here, this FSC is stress. Stress divided by strain is equal to what? Young's modulus of steel, E. Capital E is what? Young's modulus of steel. So Young's modulus of steel is what? Okay, stress divided by strain. So this is strain. What you are seeing, this is strain. Okay, so stress is equal to strain into Young's modulus of steel. So FSC we can calculate from this. FSC is equal to 0.0035 into bracket XU minus D dash divided by XU max into Young's modulus of steel. Okay, this is already known. 2 into 10 raised to 5 Newton per mm square. So XU max we are going to calculate. Okay, so D dash will be given. So we can calculate FSC. So FSC is substituted here. Okay, AST is already calculated in the third step. So we will get this ASC. So now what is ultimate moment of resistance of the doubly reinforced beam? So total MU is equal to MU limit or MU1 plus MU. Okay, plus MU. So that will going to give MU limit, that is total MU is equal to MU limit or MU1 plus MU2. What is MU2? MU2 will be calculated like this here. Okay, so MU2, okay, force, stress into area, FSC ASC into D minus D dash. Okay, so MU limit plus MU, this is MU2. If you add these two, the total moment of resistance of doubly reinforced section. So this will going to give the total moment resisted by the doubly reinforced beam. Okay, so please go once again the procedure to calculate the moment of resistance of doubly reinforced section. So we'll in the next session we'll start with the problems on calculating moment of resistance of doubly reinforced section. So remember these 5 steps. Okay. So thank you very much for attending this session. Thank you.